All right, back for break. We have a second set of practice problems for midterm 4. We've got a midterm 4 coming up soon, and we do have a second set of practice problems. So let's take a look at those. And so after, let me say this too. There will also be a set of review problems, a practice final available. So take a look in Canvas, and you'll find it there along with the resources for preparation for the final exam. But anyway, we've got a second set of problems. I was trying to come up with some problems that would fit nicely with the ones that we've already taken a look at. So, and I think maybe these work pretty well. So, problem number 1 is looking at a set of fusion reactions. And so let's take a look at this. It says that there are a couple of fusion reactions we want to consider. One of these is, now this is an interesting one. This is one we have not looked at. I don't think it's included in the text. Taking a neutron, combining it with lithium-6. When a neutron combines with lithium-6, the lithium actually divides. It doesn't fuse. It actually breaks into 2 pieces. Now we don't consider this fission. We tend to think of fission as stuff that happens at the end of the periodic table. So even though there's this splitting that's taking place, the intention is to then recombine things. You'll see when we get a net reaction here, the overall effect is to bring stuff together. We'll take a look at this and see. So what happens is it splits into a helium-4 and a helium-3, and then the helium-3, or the hydrogen-3, sorry, the hydrogen-3, the tritium, can be used as fuel along with deuterium. Now this reaction we've looked at. And so what's happening is we're building up helium-4s. And if we take a look, well, it's going to ask us to get the Q value. So let's do that. Let's go ahead and get a Q value for each of those reactions. So again, the first reaction is a neutron combined with lithium-6. It does resemble fission type reactions, right? So it splits into 2 pieces. It splits into a helium-4 and a hydrogen-3. Now, I looked up all those, the masses are here. Yeah, this problem is really long because we got all these masses. Now, a bunch of stuff is listed there. I don't think all of it gets used. I think you gotta be, let's see, I don't see hydrogen-1 showing up anywhere. Hydrogen-2 and 3 are both there. Helium-3, no, I don't see any helium-3. So it looks like hydrogen-2 and 3, helium-4, and then lithium-6. Lithium-7's not there either. So I just put a bunch of extra stuff in there, and then you guys can pick out what's relevant and ignore what's not. So I put in the mass of the neutron, the mass of the lithium-6, mass of the helium-4, mass of hydrogen-3, and the Q value worked out to be 0.005136 atomic mass units, which I quickly converted into MeV and got 4.784 MeV. So that's a pretty good amount of energy. What's driving that? And the lithium-6 is not, it's not radioactive. I mean, it's a stable isotope, but it's not as stable as some surrounding isotopes. I think we've talked about this in class, where we found that helium-4 is really, really, really stable, and then there's not really any isotopes of lithium, beryllium, or boron that are especially stable, and then carbon-12 is really stable. So there's a bit of a gap where there's nothing especially stable, and lithium-6 and 7 are examples of that. There's 2 stable isotopes of lithium, but neither has especially high binding energy per nucleon. All right, so we did end up releasing energy from that reaction. Now this one we've seen in the textbook, adding deuterium and tritium together to come up with helium-4 and a neutron. Now notice, this is kind of like fission again. We're generating neutrons in the reaction. Those neutrons are being used to set off additional lithium. So as we generate neutrons, the neutrons get absorbed by the lithium that is present, so we can combine those 2 reactions together. Now, before we combine them both together, let's get the Q value on this lower one. So hydrogen 2 and hydrogen 3, neither of those isotopes are especially stable. And when we take those and convert them into helium 4, which is super, super really stable, along with a neutron, that releases a lot of additional energy. So that's at 17.5. So those are some really nice numbers in terms of energy released in these reactions. So the problem here is saying, what if we ran this in a power plant? Now, we don't have any fusion power plants currently. We're having enough difficulty just getting hydrogen fusion to be sustainable. But, you know, you could imagine at some point maybe bringing lithium in as an additional fuel, although lithium is fairly scarce and we've already got lithium, you know, such a vital part of our battery technology and energy storage technology. Anyway, this is one of those options out there. So if we combine these two reactions together, which is what they say to do in part B, this is kind of like we did with, remember with nuclear fusion inside stars. We listed all the reactions going on for the nuclear fusion going on inside stars, and then we were able to combine them into one net reaction and get an idea of what the total energy release would be for that. And so that's what we're doing here. We're combining those two reactions. The neutrons are on both sides, they drop out. The hydrogen 3s are on both sides, they drop out. And the net reaction is taking, you know, a couple of modestly stable isotopes, hydrogen 2 and lithium 6, and forming two really, really stable helium 4s. And that's a lot of energy that gets released in that reaction. Now in part C, it says, what if we did this in a power plant? How much lithium 6 would be needed? How much deuterium would be needed every year? So if we're operating now that's an enormous power plant. That's 2 gigawatts. So that's 2,000 megawatts. That's a pretty good sized power plant, nuclear power plant. So if we took that amount of power, multiplied it by an entire year, it's saying each year this power plant puts out 6.3 10 to the 16th joules of energy. Now, it doesn't say include any thermodynamic efficiencies, and so it's probably only going to be, you know, maybe 30% efficient, but we're ignoring that right now. So assuming this somehow is 100% efficient, we can take that amount of energy that we're producing each year, convert that back into MeV, and then take the 22.4 MeV, that's our Q value, and set that equal to one reaction. So every reaction we run gives us 22 point, there's a decimal in there, right there, 22.4. And then what we can do is count reactions. We can say that 1 mole of reactions would be Avogadro's number, and then for every reaction we run, we're going to need 1 hydrogen and we're going to need 1 lithium. So this is the number of moles of hydrogen 2, deuterium, and lithium we are going to need. So 29,250 moles of lithium, lithium 6 in particular, would be 176 kilograms. Now again, lithium in nature exists as a combination of lithium 6 and lithium 7, so we would have to isolate the lithium 6, or maybe, you know, if the reaction is efficient enough, we just throw it all in together and the lithium 6 reacts and the lithium 7 doesn't. But in either case, the amount of lithium 6 specifically would be 176 kilograms. The amount of deuterium that we would need, the amount of hydrogen 2, again, we would need the same number of moles. So 29,250 moles. The molar mass of deuterium, 2.014 grams. And that means only 58.9 kilograms of deuterium. So it's just a few hundred kilograms of lithium and deuterium combined, and we could operate a really large nuclear fusion reactor for a year and generate a lot of electricity. So, nuclear fusion. Now there are neutrons being produced. That's a bit of a concern here. If the neutrons are used in the reaction, which is what we want to do, then that works out fine, I suppose. The stray neutrons are going to get absorbed by different materials. Maybe they become radioactive. So that's a concern if we're generating a lot of radioactive materials. Anyway, that's a good example of the type of problems that we've seen in chapter 42. So looking at fission and fusion power plants, here is a fusion power plant. All right, let's questions on that. Let's move on to the next problem. In problem 2, we are asked about a nuclear reaction. Now this was the early part of chapter 42. The reaction we're looking at is a proton being, probably fired into a bunch of carbon-13, and then there's a reaction that takes place. The proton comes in, reacts with the protons and neutrons in the nucleus of the carbon-13. The electrons are just spectators in these reactions. The nitrogen, the protons and neutrons rearrange in a way where a neutron is released and probably carries away a good amount of the energy, and we're left with a nitrogen-13. So we have, through this reaction, we've converted a carbon-13 into a nitrogen-13. We have created a different nucleus, and that means we've ended up creating a different element, a nucleus with a different number of protons. So what it says here, and this, I feel like this probably represents too the examples we've been looking at in class and some of the homework problems. Calculate Q for the reaction. Calculate the potential energy barrier. Now the proton is positively charged, so is the nucleus of the carbon-13. The carbon-13 has a bunch of protons in there. So the reason fusion reactions aren't going on all the time is because we have a potential energy barrier between the different nuclei. The nuclei have a bunch of positively charged protons, and to get the two nuclei really close to each other, the electrons in atoms and molecules are really spread out, as we've learned back in the chapters, in earlier chapters on atoms. And that means that by the time the two nuclei are reacting, the surrounding electrons don't have much of an effect. They're not really holding the two nuclei together that close. And so it's really up to whether we can overcome this potential energy barrier. So let's take a look at this. So first of all, here's the reaction, and as we've looked at in examples, in order to charge balance and get the correct number of electrons accounted for, what I've done is I've used, instead of a proton by itself, I've used hydrogen 1. So I'm going to use the mass of hydrogen 1, which I can look up from page 1, the mass of carbon-13, which is given, mass of nitrogen-13. And the Q on this worked out to be, it's negative. Now what is a negative Q? And it's negative by 3 MeV. It says this reaction, at the end of the day, is going to require energy. So if we do an energy profile here, the hydrogen, or the proton, and the carbon-13 are actually more stable than a neutron, than a neutron and a nitrogen-13. So these guys, if we add up their masses, are lower in mass, and these are higher. So I'm trying to generate something that has more mass in it than what I started with, and that means we are going to have to put enough kinetic energy in to the reaction to get this to happen. Now, let's see, I think it's not looking promising, right? Because it says the protons are only coming in with 2.5 MeV of kinetic energy. So at this point we're thinking, no, it's not going to happen. There is not enough kinetic energy to create something with that much additional mass. I don't have enough kinetic energy to create the extra 3 MeV of mass that we're going to have to generate. The 3 MeV in mass corresponds to this amount in terms of atomic mass units. Now, the next question they ask is, well, what about the Coulomb barrier? How large would the electric force barrier be between these two nuclei? And so the potential energy, the electric potential energy formula would be K Q1 Q2 divided by R. Q1, let's say, is the proton that has 1 charge. We got to redo this problem. The charge on the, oh no, we don't. I'm sorry. I was thinking lithium again, but we're not doing lithium. We're doing carbon. This looks fine. So Q2 is going to be 6. That's how many protons we have in the carbon. So the barrier we're specifically overcoming here is the 2 nuclei that we're starting with. Now, we know for the formula here, we have to get the Q's. We did that. 1e and 6e. That gives us on top 6 times Ke squared. And Ke squared is one of our shortcuts, 1.44 MeV times femtometers. Now, we got to get the denominator. We got to figure out how much distance is there, center to center, when these 2 nuclei just touch. And so what we do, and again, we've seen examples of this in class, we're looking at the 2 radiuses, 1.20 femtometers times, well, for the proton, that's just 1 nucleus, or 1 nucleon to the 1/3. For the carbon-13, I have to include all 13 nucleons to estimate what the radius for that would be, and so that would be 13 to the 1/3 power. For R1, we're getting 1.2 femtometers. For R2, we're getting 2.82. We can add those together. It says that it's just over 4 femtometers, center to center, that we need to bring the 2 nuclei within. So putting that into the denominator, it says in order for the reaction to take place, the nuclei need to be this close by our definition of center to center distances. And the electric force potential energy formula then says it would be 2.15 MeV. Now, we do have enough kinetic energy in the proton, 2.50, to overcome that 2.15 MeV barrier. So there is enough potential energy, assuming that all of the 2.50 MeV in the protons is available to bring the 2 nuclei near each other, then we do have enough for that. So in part C it says, okay, what's going to happen here? Will these protons have enough energy to set off this reaction? They may have enough energy to overcome the potential energy barrier, but they're not going to have enough to meet the Q requirements. So that's just not going to happen. They're not going to have enough energy to create the nitrogen-13, so it won't happen. We're going to have to send in protons that have higher energy. All right, so good example of looking at the Q values. How do the masses differ from before and after the reaction? And then within the reaction itself, what is going to be the repulsive electric force that we have to overcome, the electric potential energy that we have to overcome in bringing the 2 nuclei close enough that they can react. All right, so I guess that takes us through problem 2. Let's go ahead and take a look at problem 3. So the first 2 problems were coming from chapter 42, and now we're going to look at something from chapter 43. We are going to look at the decays of what's called the tau lepton. Now, if you remember back from chapter 43, there are different generations of the quarks and the leptons. there are 3 generations of electron-like particles. There's the electron, there's the muon, and then what's called the tau. And the tau is the heaviest of these, and it tells us here, here we go, the tau is really at a large mass here, 1,776.9 MeV, and one of the possible ways a tau can decay is into a pion and a neutrino. Now, as you get heavier and heavier, typically there are more and more options for decay, and that's true for the tau lepton. So there's 20 or 30 different ways the tau lepton can decay, and it does turn out that decaying into a pion is, it's one of the prominent ones. It's probably 10% of the time or so it's decaying into a charged pion and a neutrino. All right, so here's kind of the reaction here, or the diagram. So the Feynman diagram would look like this. The tau is a lepton, so in order for the tau to decay, it's going to change into its neutrino. So there's a tau neutrino. So we're looking at in the 3rd generation of leptons here, and we're generating that tau neutrino. And that means that the decay has got to be a weak decay. Now, I know we've looked at a lot of examples of using W plus, W minus for these reactions. And that's because in many of these, I'm going to say more common types of reactions, it's the weak interaction that becomes very important in enabling particle decays to take place. Now, what we would have then is that the W then would couple to a pair of quarks, or more specifically a quark-anti-quark pair, and because what we're trying to generate here is the pion, and we're told that the pion, it's a meson, it's a quark-anti-quark, and it's anti-up and down. So this is the pion here. So I put in all the gluons to show how those 2 quarks are combined, and then I ran the quark line backwards in time for the anti-quark and forward in time for the quark-quark. And that's the Feynman diagram completed. Now in B, it asks about conservation here, and so it says show whether or not quark and lepton flavors are conserved. And hey, the tau's turning into a neutrino, a tau neutrino. Those are 2 different lepton flavors, so that's not conserved. And the 2 quark flavors connected together here are ups and downs. So I could think of this, if I follow the arrows, as the anti-up becomes down. The flavor goes from an up quark going backwards in time to a down quark going forwards in time. That flavor is not conserved either. In order to be conserved, the tau would have to still be the tau on the other side, lepton, and the up would still need to be an up. But those flavors both changed. All right, now we can take the tau lepton, since it's only decaying into 2 particles, we can use the formulas we've developed for 2-particle decay. So here's the tau. Let's have it start at rest with a mass of m naught, and then it decays into these other 2 particles. Now, all of the neutrinos, even the tau neutrino, we're going to list as 0 MeV for the purposes of this problem. These are not, the neutrino masses are known roughly, but, and we know that they all have mass, or at least there are indications that they all have mass, and that they're very low. So this is really an approximation that we're using. The pion is at 139.6, so that's how the masses compare. Let's see. So the Q value for this reaction is the mass of the tau minus the masses of the, what does that say? Does that say minus plus? It's just plus. Oh, this is the minus goes with the pion. Sorry, that's a little confusing. So the 2 masses together, and that leaves us a lot of kinetic energy. So a lot of energy is going to be released in this, right? The mass of the pion is so much smaller than the tau, these two particles could be coming out with a lot of energy at really high speeds. When we do the kinetic energies, and this is using the formulas that we've worked from before, the kinetic energy, let's say that the pion is particle 1, its kinetic energy, putting in all the masses carefully, works out to be, well, almost half of the available energy. And what about the neutrino? Well, the neutrino, about 54%. So it's actually pretty balanced. Now, why is that happening? Doesn't the neutrino have much, much lower mass? Shouldn't it be getting a lot of the energy? And this is happening because the tau has so much mass and so much kinetic energy is going to be released here that it's enough for both of the particles. These other masses are low enough, the pion's mass is low enough that it's almost becoming kind of like a massless particle. Anyway, but it's not 50-50. It's 46% for the pion. That leaves it with 754.3 MeV, and then for the neutrino, 883.0 MeV. We can calculate the speeds, so they want us to come up with the speeds from this. For the pion, we can use a gamma calculation, 1 plus the kinetic energy, and it says, yeah, the pion actually is going to come out at a gamma of something like 6.4, and plugging that into our formulas from special relativity says that the pion's going to be going 99% the speed of light. So the pion is coming out at a really high speed with lots of kinetic energy. And, you know, if we're assuming the neutrino is massless, then we're also assuming that it's coming out very, 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 very close to the speed of light. So we'll just estimate it as coming out at the speed of light. Okay, so lots of mass in the tau compared with what it's decaying into, and that's resulting in really high speeds for those two particles. Now, the last part of this problem, part D, is saying the pion has a lifetime. So on average, how long does the pion survive? Because the pion itself, we've seen this, right? The pion decays also. So the pion decays either into a muon in a neutrino or an electron in a neutrino. So we've seen examples of pion decay. It only survives for 26 nanoseconds. How far could the pion travel on average before decaying? Well, there's a time dilation effect here. Because the pion is being generated at a gamma value of 6.4, that's going to boost the amount of time that it survives on average. So in the laboratory reference frame, instead of surviving for 26 nanoseconds, that sounds pretty short, it's going to last 6.5 times longer. It's going to survive for 166 nanoseconds. Now, if it's traveling at 90.9877 times the speed of light, that's its V, and it's going to survive for 166 nanoseconds, it says it can go 50 meters. So you would think, wow, just, you know, its lifetime is 26 nanoseconds before we did the time dilation effect. And then after the time dilation that got longer, that's enough to travel 50 meters. So that's going to be easily observable in a particle detector. So if we have a particle accelerator and we're running these reactions, we would be able to easily pick up the pion. It's going to travel long distances during that time. All right, questions on any of this? All right. So, you know, any questions at all, stop by office hours and we'll get those looked at. So yeah, I'm glad I have these extra set of problems now. The last problem that we have, the very bright star Rigel is located in the constellation Orion. Now you don't have to know that for the midterm, but it may be some of you are familiar with the constellation Orion. It's one of the best known constellations, along with maybe the Big Dipper, and it has two really bright stars, Rigel and Betelgeuse. And Rigel is located 860 light years away, has a surface temperature of 12,000 Kelvin. So it's a really it's a blue star. It's a blue violet star. It's an ultraviolet star. The surface temperature is so high. Now it has a diameter of 110 million kilometers. So that's a spectacular set of numbers for this star. What is the observed parallax angle for Rigel? This is the data that we've collected. So what would be its parallax angle we would measure from Earth? What would be the peak intensity? What would be the wavelength of peak intensity for the light? What would be Rigel's luminosity? And what would be the observed intensity of starlight reaching us here on Earth in this star system? What would be the intensity of the starlight from Rigel? Okay. And then on part E it says, what if there's another star, just the very same type star as Rigel, but it's placed twice as far away? What would happen to all the numbers? So the parallax, we can put that as in terms of 1 AU, the parallax angle, 1 AU divided by the distance. Now the distance here, the units don't match up yet. So the parallax angle is defined in terms of the base distance for the Earth's orbit around the Sun. And so we have to use 1 AU. So we just have to convert. So I can put in a conversion factor. Every light year we said is 63,000 astronomical units, AU. And that says that the angle then of parallax for Rigel would be 1.85 10 to the minus 8 radians. That's tiny. That's down into the nano radians. If we convert that into degrees, it's about a millionth of a degree. 1 degree of arc divided into a million pieces. That's how much Rigel shifts back and forth as Earth orbits the Sun. And that's actually measurable. Yeah, that's I'm going to say well within the capabilities of parallax measurements currently. And so the angle here would be, if we put it in arc seconds, 0.00381 arc seconds. So check all those, check all your conversions. Now as far as the peak wavelength, the peak intensity wavelength, if it's at a temperature of 12,000 kelvins at the surface, its peak wavelength it's in the UV. So the Sun's peak wavelength is, I got to be careful here. I guess it is in the visible, So the Sun's peak intensity is kind of in the middle of the visible part of the spectrum. The peak wavelength here is the surface temperature, just compared with the Sun. The Sun's surface temperature is around 6,000 Kelvin, so we're looking at twice the temperature. And at double the temperature, the wavelength will be half, the peak wavelength will be half as much. All right. In terms of luminosity, we can use the surface intensity, which is related to surface temperature. So we've got a surface temperature measurement by looking at the spectrum of light. And we've got, actually, did we get a diameter on this? We did, right? Yeah, 110 million kilometers. Now, the distance from the Sun to the Earth is 150 million kilometers. So Rigel is big enough that it would reach most of the way, if it were placed where the Sun is, it would reach most of the way to Earth, and it would have twice the surface temperature. So Earth would be really, really warm if that were the case, if we were to swap the Sun for the star Rigel. Let's see. So putting all these numbers in, so we were given a radius to work from, so we converted that over into, now that's in terms of billions of meters, that sounds right, and putting that into the formula, and I guess, so this is all done. I kind of skipped a step here. The 4 pi r squared is all put in as one number here. The Stefan Boltzmann times temperature to the fourth is all combined here, and then putting those two together. This is the surface intensity times the surface area. That gives us 4.6 10 to the 31 watts. Okay, so that's an enormous amount of watts. How does that compare with the intensity of the sun? Well, the sun's luminosity is about 4 times 10 to the 26, I think is it. So this is like 100,000 times the luminosity. It generates energy at 100,000 times the rate of the sun. So no, not all stars are identical. Rigel started with an enormous amount of mass. The nuclear reactions taking place on Rigel much more intense than the nuclear reactions taking place inside the sun. That's a lot of luminosity for a star. Now, we're supposed to calculate, well then, what would the intensity be by the time the light reaches Earth? Now, the light's spreading out in all directions, and that means the intensity of the starlight from Rigel is going to drop off with distance. And so we can take that total luminosity, divide through by a surface area, but the surface area this time is going to be at a distance of 860 light years. All the way to Earth is the distance that we're working in terms of. So that's a lot of surface area. The intensity then for the, this is the luminosity, so this is the distance, and the distance gets squared. Yeah, I was just checking again. I could have added a step here. I could have added a step here too. So this distance gets plugged into here. Now that's 8 times 10 to the 18th, but that's going to get squared. And so the intensity of the light reaching us from Rigel. So if you've ever wondered, what's the intensity of a bright star in the sky? This is one of the brightest stars in the sky. 55 nanowatts per square meter. So, that gives you an idea of the sensitivity of your vision. If I'm looking at the sky and this star looks pretty bright, the intensity of that light's, it's down in the nanowatts per square meter. So, and that actually looks pretty bright. Now, what would happen with all these numbers, with the parallax, the peak wavelength, luminosity, and intensity observed from Earth, if we took Rigel and made a duplicate and placed it twice as far away? Because there's other stars like Rigel out there. It's just Rigel has these remarkable numbers in terms of luminosity, and it's relatively close to Earth. So if we moved it twice as far away, the parallax angle, that distance would double, and that means that the angle would be half as much. So parallax would drop, parallax angle would decrease by a factor of 1/2. The peak wavelength won't change, right? The surface temperature is unaffected. That's an intrinsic property of the star, the light coming off of the star. So that would stay the same. And then the overall luminosity would also stay the same. If it's an identical star, it's going to be just as luminous. It's going to be producing energy at the very same rate. And then finally, what would happen with the intensity? Well, intensities drop off like distance squared. So this would actually go down by a factor of 4. So the luminosity would drop from 55 nanowatts per square meter down to 13.9. It'd still be a bright star in the sky, even if it were twice as far away. All right, so we've got those, couple sets of practice problems for the midterms, and of course the format here. This was an exam that was given during a previous semester, and so that gives you an idea. It's a good set of problems. I feel like this is a set of problems that you should be able to work through pretty well. This should feel fairly familiar after the examples we've looked at, and the lectures and the homework and everything. And it gives you an idea of what would be expected during an exam. So if you've got questions on these or any of the homework problems, stop by office hours. Good luck with midterm 4 that's coming up. Again, if there's anything I can help out with the preparations, let me know.